Hi guys.
Hello.
Okay. Okay, we'll give it a minute for other people to join up. Before we continue on with chapter 6.4, which is not on the homework and that's due today, and not on the quiz that's happening this afternoon. The homework I know includes 6.4, that homework packet. It's 6.2, 6.3, 6.4, so you can ignore the 6.4 part. Hang on. The next week when I post the homework that will include 6.4, it's going to be the same packet, so you can ignore 6.2 and 6.3 next week when we have 6.4 that needs to be done. So you guys can get a jump start on the 6.4 homework this weekend because you will already have it. So let's see, I'll wait for everybody to arrive, and then I just got an email from the president of Northeastern. It looks like a blanket email. I don't know if you guys all saw this too. It looks like they're going to suspend classes on Monday, June 8th. Did you guys all get that email?
Yeah, I saw it.
Okay, so I guess I guess we're not having class on Monday. So we can I can post a video if you want of stuff, or we can just wait and then meet up on Tuesday again. How would you guys like to do that? What would you guys do? You want to think about it and then let me know? I guess if they're suspending, I'm like admitting people into our room. They're suspending classes on Monday, so I guess we won't have class on Monday. But if you guys would like, I can post the video for like the lecture for that day, and you guys can watch it on your own, or we can just pick up where we left off on Tuesday. Let's see. So
the video being posted works well for me.
Video posted. Okay, anybody? You guys can write in the chat. I've got the chat room open if you guys want to say what your thoughts are for Monday. So it looks like what we would have for next week is chapter 7.2, T distributions to 7.2, 7.3, 7.4 we need to cover, and then chapter 9 we're starting to cover. I agree, like the video for posted on Monday. Okay, so I can make a video. I'll make a video then for chapter 7.2, and then I'll post it so you guys can see it, I guess, when our class time would have been, or I'll just post it on Monday morning, and then you guys can watch it, and then we'll reconvene, I guess, on Tuesday. So it'll be kind of like what you would have seen if we were to have had a class, but we won't have a class. But I'll make a video for it, so then you guys can get the material, and then we'll kind of pick up where we left off then on Tuesday. If anybody else, you guys can write into the chat, or you can send me an email if you have a strong opinion and you don't want it to be on the chat line. That's fine. You can decide. So let me know. But otherwise, if I don't hear from you, then I'll make a video for the next chapter section, and then I'll post that. I'll put an announcement too to let you know when the video's been posted, so you guys can take a look for that on Monday. I like the video too. Okay, good. All right. So far, looks like we're getting votes in for the video. So we'll go for that. All right. So apparently, there's no formal class on Monday, but I'll make a video for that chapter section, and I'll post it on our lecture videos page. But I'll post an announcement to let you know when the video is up, so that you can take a look at it. All right. Okay, guys. Can you go over which homeworks are due tonight again? Yes, exactly. So let's just write that down really quick. I'll do that on a separate. So let's write this down here so we can see. So the homework, and this is also what's going to be on the quiz. Right. So the homework and the quiz. So this will be, so we had the stuff that we've been covering since our test. So this is going to be chapter 5.3, 5.4, 6.2, and 6.3. Okay, so these are all things, these are homeworks that are due today. The homework packet you'll see has 6.4 on there, but you can ignore that part. That'll be, it's just kind of how the PDF of the homeworks all, somehow all got saved together. Anyway, 6.2, 6.3, 6.4 are on the homework packet, but you only need to do 6.2 and 6.3 for today of that packet. But what's to do is 5.3, 5.4, 6.2, 6.3. Okay, and that's also where our quiz is. We'll cover those topics as well. So they're actually related. There's the interval estimation. That's our confidence intervals. That's 5.3. Properties of estimators. That's basically looking at biased and unbiased estimators. That was pretty short. hypothesis test 6.2, and then 6.3 is the hypothesis test using binomial data. So 6.2 and 6.3 are really related. One is using normal distribution continuous data, and 6.3 is using binomial data. Okay, so we're doing the same kind of hypothesis testing, but one is using continuous values, one is using a proportion. Okay, what we can do is today I'm going to finish up our stuff for chapter 6.4 today, which won't be on the quiz, but it's also good, you know, to kind of help you think about things. I'm going to finish up chapter 6.4 in terms of our examples, and then I can open it up to, if you guys have questions about various homework problems, I'll stop the recording when I'm done talking about chapter 6.4, and then if you guys want to ask questions about the homework, then we can go over those. Okay? All right. So any other quick questions that you guys want to ask before I finish up 6.4? We're going into like power curves and all that. Okay, I'm not seeing anything on the chat. Okay, so I'll wait till the end when I'm done with 6.4. Okay, so this is the lecture examples for 6.4. Okay, type 1, type 2 errors. Okay, example 3 is an interesting one because we've been talking so far about probability density functions that are based on the normal curve, right? So that's our bell-shaped curve. Okay, so when we're using a probability density function, our fy, okay, our function of y, or f of x, whatever our variable is, and we're using that 1 over 2 pi times sigma e to the minus 1/2, you know, so on and so forth. That's our bell-shaped curve. And because we're using the bell-shaped curve, we can use our lookup table because somebody went through the trouble of integrating all the different values and came up with all the areas under that curve. So that's the great thing about the normal distribution, but it's possible to have a probability density function that's not a normal bell-shaped curve. And that's what example 3 is. So we just kind of want to take a step back really quick and do something. This is, so right at the top, this is non-normally distributed data. We've got this probability density function here, f of y of the and theta plus 1, y to the theta, you know, y is between 0 and 1, and we've got our hypothesis here. Okay, so our hypothesis, null hypothesis, is theta equals 2 versus theta 1. Our alternative is that the theta is greater than 2. So this is going to tell us this is a one-sided test, right, with the theta being greater than 2. Although that doesn't really matter so much at this point because we don't have symmetry anymore, right? I'm dealing with this kind of a curve. Okay, if I think about theta as being some kind of a value, some kind of parameter, okay, this is going to be maybe some kind of a, you know, polynomial-ish type of equation. Okay, so our decision rule is this. So we're going to record x. X is our, you know, the number that we're looking at, but x represents the number of samples, y sub i's, that exceed 0.9, okay, and we're going to reject our null hypothesis if the number of samples that exceed 0.9 is greater than 4. Okay, so these are two different numbers. 0.9 is the value for our y sub i. Okay, remember our y's go from 0 to 1. Okay, so these numbers that exceed 0.9, right? We want to count up how many of those are, you know, how many of those do we have? Do I have 1? Do I have 2? Do I have 3? Do I have 4? Well, the minute I have 4, I'm going to reject my null hypothesis. Okay, so what proportion of the time will this yield a type 1 error? Okay, all right, so let's go ahead. Whoops. Go ahead and start thinking about how we're going to set this up. All right, so let's write down what we have and what we're going to think about. So alpha is the probability that y, oops, sorry, this is, let me write this down in words first, that we're going to reject the null hypothesis given that the null hypothesis is true, right? That's our type 1 error, that's alpha, okay? So let's write down, so x is our binomial random variable. It's a binomial random variable because the question is, does it exceed 0.9, yes or no? So x is the binomial random variable. Y is our continuous random variable, right, where it's going to be between 0 and 1, but x is our binomial random variable. Okay, and then, and I think, do we have, why am I saying I've got n equals 7? So I'm going to write down in my notes, I've got n equals 7 here. So we'll see where this is coming up from later. So we've got x is our binomial random variable. I've got n equals 7 as possible. Oh yeah, sorry, a sample of 7 observations. I'm not reading my own problem. So n, the number that we have is 7, okay? So P is the area under our probability density function, which is this, Fy, y theta, theta plus 1, y to the theta. And then this goes 0 from, y goes from 0 to 1, okay? So the probability under our PDF, so before we've been thinking about our probability density function, our PDF, as being a normal shaped curve. And the probability is the area under that, you know, from whatever z less than, you know, some value. Okay, but now we've got this as our PDF. Okay, so it's a non-normal distribution. Okay, so now what we need to think about is Fy, y of theta, when theta equals 2. So this comes from my null hypothesis. Okay, so when theta equals 2, I'm looking at Fy, y of 2. Now when I have theta equals 2, I plug theta into my PDF, I get 2 plus 1 times y to the 2. So this is 3y squared. So I'm looking at my PDF is a parabola, right? So my PDF looks something like, it's a parabola, okay? So if we go from 0 to 1, then you can imagine, you know, how high up this is going to be. So this is our PDF when theta equals 2, okay? So now I'm going to start writing more. So our little p is the probability that y is greater than or equal to 0.9, given that h naught is true. Remember, our h naught, right, our null hypothesis is that theta equals 2, okay? So this looks like the probability that y is greater than or equal to 0.9, given that Fy sub y 2 equals 3y squared. Okay, so when h naught is true, that means theta equals 2. So this is our PDF right here, if h naught is true. Okay, so if this is true, that's what I'm going to be using to see what I get in terms of my probabilities. So I'm going to have to integrate 0.9 to 1. This function here, 3y squared dy. Why am I doing 0.9 to 1? Well, that was, right, part of our random variable is that our y sub i's are going to exceed 0.9. So I can only go up. My maximum value for y is equal to 1. So I'm checking to see, right, what's the area under the curve, basically from here to here. If this is 1, then I'm going to go from 0.9 to 1. Okay, so I'm looking for those values. So when I do that, I get y cubed from 0.9 to 1. And then when I evaluate that, I get 0.271. That's a 0. This is a probability, remember, so it should be between 0 and 1. If you're getting some number that's negative or some number that's greater than 1, that should be a red flag that, you know, maybe you've set things up wrong or you did calculate some of the calculus problems wrong. All right, so now my alpha value I have to think about is my probability that my random variable x, this is part of my problem, is it greater than or equal to 4, given that theta equals 2. This is our null hypothesis, right? So now I have to sum these up. So this is k equals 4 to 7, okay? 7 choose k, 271 to the k, 1 minus 0.271 to the 7 minus k. Okay, so I have to sum all these up. Okay, so this is why alpha, this is the probability of making a type 2 error alpha, right? This is our decision rule. Okay, x is greater than or equal to 4. So I can only have 7 observations total, okay? But I want to know, of those 7, you know, do I have like more than 4 that are going to be, you know, satisfying this rule here? So that's what we're looking at. I don't know which 4 out of those 7. I have, you know, samples, you know, 1 through 7. So it could be samples 1 through 4, or it could be 2 through 5, or it could be, you know, any combinations. That's where our combinatorics comes into play. This is the probability, essentially, of one of them equaling that, okay, being from 0 to 9. Now this is of those 7 samples, okay, using this probability of one of them, and this deals with the combinatorics of it all. So I'm going to add these all up. So this is going to give me my alpha of 0.092. That's our alpha. Okay, so what does this mean exactly? This means that H naught will be incorrectly rejected about 9.2% of the time. Okay. Incidentally, this alpha is kind of high. right? Remember, we like to see alpha being less than or equal to 0.05. Okay, 0.05 is the typical value for our alpha, right? That's like, you can think about that as our 95% confidence interval. Alpha's, less than or equal to 0.05 are good. 0.09 is pretty high. So the question was, what proportion of the time will this yield a type 1 error? So about 9.2% of the time, because alpha is our type 1 error. Okay. So it's just to show you that you can have a PDF, okay, other than a normal distribution. If you have it other than a normal distribution, then you have to integrate it yourself to find the probability of, say, one of those things happening. Now we have to apply that to our random variable, which is between 4 and 7, right? Greater than 4, no more than 7, because I only have 7 samples of it happening. Okay, getting a value that's between 0.9 and 1. Okay, so it's possible we can do things that are not normally distributed, right? Depending on the data, depending on the problem that you're working on, right? Maybe your probability density function is going to be a Poisson underlying function, okay? But all of the Poisson data actually kind of looks like a normal curve at some point too. I'm going to draw up a lot of what these curves look like. At some point we'll kind of post them so that you can get a feeling for what they look like. But it is possible that your density function could be something other than, this is parabolic, could be something other than, a normal curve. More likely than not, okay, most data in the real world, especially if it comes from a binomial data set, which is this yes or no type of an answer, okay? When it comes from a binomial data set, then more likely than not, it's going to be normally distributed, especially when we have larger n values. Okay, so I'll give you a chance to write that, and then we're going to go in and work through one full problem that basically looks at power. Okay, and I wrote it out as like part 1, part 2, part 3, part 4, because as we're working through this, we're changing various parameters and we're seeing how they're going to be affecting the power or affecting different values on what we're looking at. So we'll come up with graphs and pictures and stuff as we work that through. Okay, I'll scan this page in too and then post it later today. All right, so this is, excuse me, example 4. I'm going to start off with part 1. So let's go ahead and take a look. So this says, let X be the IQ of a randomly selected American. Okay, we're going to assume that X is normally distributed and it has an unknown mean and it has a standard deviation of 16. So it's a little academic, right? Because we normally, if we know what this population standard deviation is, we're going to know what the population mean is. But as we move along in these chapters, we'll see how we can work through these problems when we don't know what the population mean and we don't know the population standard deviation. For now, we're just kind of pretending. All right, so now what we want to do is the first part, we're going to take a random sample, n equals 16, and we're going to set alpha equal to 0.05. So this is the probability of committing a type 1 error. We're going to test the null hypothesis, right? So this is a one-sided test. Our mean is equal to 100 versus our mean's greater than 100. And then we want to find out what's the power of the hypothesis if the true population mean is equal to 108, right? So what we're going to do is we're going to derive the power. We're going to come up with a power curve, okay, assuming that the true mean is somewhere along here. We're going to graph these things out so that you can see what these things look like. Okay, so let's start off like we always do. We're going to state what our hypothesis is. Okay, so my hypothesis states, my null hypothesis says my mean, we have it written up there, but let's write it, versus, oops, sorry, U is greater than 100. Okay, so this is going to be a right-tailed test. So I'm just going to quick draw that out. Need to come up with our critical value too. Okay, so our critical value alpha, they gave us at 0.05. This is right-tailed. So I don't need to cut alpha in half to figure out what my z value is, right? So if it's a right-tailed test, so here's our mean at 100, and then this right here is going to be alpha. That area under the curve, okay, is going to be alpha. So I need to figure out what the z value is. Okay, that's going to give me that, right? So I just look up on my table for where the probability equals 0.5. So I find z alpha is equal to 1.65. It's positive, right? Because we're on the right-tailed portion of it. So here we are. Okay. in the table. Okay. So now what I need to do is scroll this up here. So my question is, what is the mean when z is equal to 1.65? They didn't tell us what the mean is, right? It's an unknown mean. So we want to figure out what's our possible mean. Okay, so we're given some kind of a sample, like a possibility. That's our 100. But where's our population mean? Where could it be? So what I'm going to do is I'm going to say z equals x bar minus mu radical n. Okay, so I'm going to go x bar minus 100 over 16. My I was given, let's see, standard deviation of 16 and then a sample size of 16. Okay, so I plug this in and I'm going to get, oh, and this is equal to 1.65. So when z equals 1.65, what's our mean going to be, our sample mean? So we want to find out, like, where's that critical point, right? Where's that x bar value that's going to tip us over into our critical point here? So when I solve for this, get x bar equals 106.58 here. So I'm going to write that in. So this value here, 106.58. Okay. That's associated with the z alpha of 1.65. Okay, given all these other parameters here, given our mean at 100, given that's our hypothesis. This is our null hypothesis, and then our sample size and our standard deviation. Okay. Right, so now part B says what we want to take a look at. We're not fully answering all this stuff because we're dealing more with power and other types of things. So power, we want to take a look at. This is the probability of rejecting our null hypothesis when the mean is equal to 108. So this is when we're saying our true mean is equal to 108. So my power is going to equal to the probability that x bar is greater than or equal to 106.58 when our true mean is equal to 108. Okay. Okay, so let's see. This is let's write this out. So this is probability z greater than or equal to. So I'm going to go 106.58. That's my critical junction point, right? Minus 108 all over 16 over radical 16. I'm still dealing with the same sample that I had before. This is the probability that z is greater than or equal to minus 0.36. Oh, it's a minus. So what does that mean? If it's minus, remember on our power curve, right? On our power curve, we're dealing with, draw this out. This is like saying our true mean is equal to 108, right? And then we're now looking at here, this is our z equal to minus 0.36. So this is where our power is. Remember, it's going to be left-tailed when we're dealing with power if our true mean is greater than our hypothesized mean, right? So you can imagine here, right, this is 100. If I drew this out, let's see if I can get this. Right, so this is my true mean is 108, right? And I'm looking for where's that spot that's going to give me my power. So my 1 minus beta, this is going to be my beta value here. That's how we want to think about it. I'm drawing a lot of pictures just so you can visualize what things look like. Okay, so let's calculate this out. So then this is equal to 1 minus the probability of z less than or equal to minus 0.36, which is 1 minus 0.3594. This comes from the table. This is where z is equal to minus 0.36, okay, here, and I'm going to get 0.6406 is the power, okay. Okay, so let's I'm going to draw out a bigger picture so you can see. Draw them both out here. I'll try to draw them big. So it's going to look like, try to exaggerate it. So here's our mean equals 100. That's our null hypothesis. Okay. And here's, oops, sorry, I drew that. I'm not trying these to scale. So this is our true mean of 108. True mean of 108. Now 106, I'll put like right about here. 106 point, what do we say, 5? 106.6. So at this spot right here, this area right here is the power. This is equal to 0.6406. Okay. So be careful. This is the curve that we started off with our hypothesis. Our hypothesis was that at the mean was at 100. Okay, 106.5 gives us the point at which we dip into critical portion. Okay, but then the difference between that critical portion, okay, where things are significantly different, and our true mean defines our power area. Okay, true mean. I'll write it here, and this is our null hypothesis. Okay, so what we're going to do is we're going to take different values, right, and we're going to manipulate and see how this changes the curve. Let me just write down, I'm going to summarize this. So this says we have 64.06% chance of rejecting our null hypothesis, which says that the mean is at 100, in favor of our alternative hypothesis, which is that the mean is greater than 100, when the true mean is equal to 108. So the true mean is greater than 100. In reality, we don't know where the true mean is. What we do is we test out various values of where the true mean could be, and we find out where the power curve, where the power is. So I mean, like, we'd like to see the power at about 0.8. That would help us come up with an estimate based on our hypothesis and significance levels, right, where our true mean might be. Okay, so we're going to do stuff like that. Okay, so you guys all, do you need time to finish writing this before I go on to other parts? Part 2?
1 sec. All right.
Great. Okay, so part 2. So part 2 says, what's the power of the hypothesis if the true mean is at 112? So we're changing the true mean. We're going to spread it farther apart. We're going to see how that affects the power. Okay, so I write down some parameters. Our alpha equals 0.05. Our z value was greater than or equal to 1.65, given that alpha value. This is our observed sample mean greater than or equal to 106.58. So I'm carrying over some parameters from before, right? So given the same alpha, which is our z value corresponding is 1.65, based on our original hypothesis was that our mean was at 100, right? So that would give us these values here. 106.58 is the point at which, given our standard deviation and all, is the point at which, right, the means become significantly different. That's how we think about this. At the alpha 0.05 level, any mean greater than or equal to 106.58 is going to be significantly different than our hypothesis, our null hypothesis. So let's write down. So our power is the probability of rejecting our null hypothesis when our true mean is equal to 112. Okay, so that's what we're trying to figure out. Okay, so now our true mean is at 112 instead of 108. So we now need to look at, right, there are differences between 106.58 and 112. Okay, so I'll write this down. So our power is the probability that x bar is greater than or equal to 106.58 when our mean is equal to 112, which is the probability that z is greater than or equal to 106.58 minus 112 all over, same standard deviation and sample size, okay, which is equal to 1 minus the probability that z is less than, sorry, this is probability that z is greater than or equal to, I got minus 1.36. So this is 1 minus the probability that z less than minus 1.36, which is going to equal to 1 minus 0.0869. This is from our table. Okay, this is the z minus 1.36, okay, which is equal to 0.9131. Okay, so let's draw that out so we can see what we're dealing with here. Okay, so now I've got, try to exaggerate. Oops. So this is our hypothesis where our mean is equal to 100, okay? And then now our true mean is equal to 112, right? So now, let's see, it's gonna be like this point here. This is 106.58, right? So this is the beginning of our critical region right here, okay? But it also is gonna be defining this region right here, gives us our power, which in this case is 0.9131. So our true mean is pulling farther apart from our hypothesized mean. So the power of our test, right, increases, okay, because the distance between them, they're definitely, like there's a significant difference between them that we can see very easily. So this here is our power, and it's defined right here. Okay, all right, so let's write out a summary. You can know what it is that we're doing. Summary, this means that 91.31% chance of rejecting our null hypothesis in favor of our alternative hypothesis when the true mean is equal to 112. Okay, so I'll also summarize that a little bit more too. So this means also that the probability is greater for true means greater than mu. So the probability increases as our true mean moves away from our hypothesis. From our null hypothesis mean, okay? And that's like saying, okay, we're probably doing pretty good. There's definitely gonna be a significant difference between them. If they're pretty close together, it's gonna be hard. There's gonna be a lot of overlap between the two. It's gonna be harder to see the differences between them. Okay. All right, let's do another one. Are you guys, let me know if you need more time to write this down, and then I'll move on to part 3. Part 3 says, we're going to make the true mean even farther apart. This is just to really exaggerate things. So what's the power of the hypothesis if the true mean is equal to 116? So we're going to do the same thing. So the same stuff from before, alpha equals 0.05, which makes our z alpha equal to 1.65, right? That gives us our critical point. So that means that our observed sample mean that puts us into the critical region is going to be 106.58. Okay, so now I need to look at the difference, the distance between 106.58 and 116, our true mean. Okay, so our power is going to equal to x bar greater than 106.58 when true mean is equal to 116. So this is the probability that z is greater than or equal to 106.58 minus 116 all over 16 radical 16. And that's equal to probability that z is greater than or equal to minus 2.375, okay, which is equal to 1 minus the probability that z is less than minus 2.375, which is equal to 1 minus 0.0089. We're starting to get close to the tail end, which is equal to 0.9911. So pretty high power. Okay, so let me draw this out in a really exaggerated way. So here's our hypothesis. Okay, and then I'm going to really exaggerate this, so bear with me here. So this is true mean. Get a really long tail. I'm really hyper exaggerating this so you can see. Okay, so now this is 106.58. So you can imagine this bit right here, huge portion of it makes up the power. Right, we get most of the curve, 99.11% of the curve. Almost the whole thing. Okay, I really exaggerated it just so that you can see. Okay, so now I'm going to summarize parts 1 through 3 into a power curve, just so you can see like what it means to plot our values, our mu values against our power numbers. We're going to keep coming back to this curve because we're going to keep changing parameters, and we're going to see how this curve is going to shift around depending on the parameters that we do. So this gives, let me just summarize this. I'll do it in green. So we have a 99.11% chance of rejecting our null hypothesis, which is mu equals 100, in favor of our alternative hypothesis, which is mu is greater than 100, when true mean is equal to 116. That's our summary. Okay. I took this, right, 0.9911, and I made it into a percent. Okay, to explain it in words. So let's come up with our curve. This is our power curve. You guys can see all that. So this is our power. Our power goes up to 1. It maxes out at 1. So I'm going to do this in tenths. 1. Okay, so here's my power curve. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.9. Okay, so these are our mean values. Oops, you can't see that. Our mean values. Okay, so I'm going to put 100 here. 104, 8, 116. Okay, so let's see our power curve. So this is our alpha value. Alpha equals 0.05, right? So this one means here. Okay, so now I've got and let's do this. This is n equals 16 and 108. I had a power of what was our first power? 0.64. So at 108, I had a power of 0.64. Right, at 116 we had a power of 0.99. Right, so this is 108 and 0.64. This is 116.99. Okay, here, and I'm going to graph this out. So it's going to go, and then it basically maxes out there. Okay, so this is our alpha equals 0.05. Okay. And our n is equal to 16. We're going to add to this table here. Oops, there. Okay. So far, so good. In the other parts, we're going to keep coming back to this table here. Kind of a long example, but it really does, I think, exemplify how changing the parameters can help you understand what happens to the power and all these other values that we have. Does everybody have this curve here? I can flip the page and start the next part.
One second.
I didn't draw this very smoothly. It's sort of like a, kind of a shape. I got this sigmoid shape.
Okay.
Okay, we'll come back to it too. All right, so part 4. So we're going to redo the test with alpha equals 0.01 and what happens to the power. Okay, so now let's write down we have, so alpha equals 0.01. our Z value now is going to be 2.326. This comes from our table. This is going to change our X bar. Okay, so that X bar was that 106.58 that we did before. That was defined as the point at which we went into our critical region. So I need to recalculate out my X bar. So my Z equals X bar minus mu all over sigma radical n. So X bar, and this is equal to 2.326. This is X bar minus our null hypothesis is the same as before, and our n and our standard deviation is the same as before. Okay, so I need to figure out what my X bar is. That's 109.34 equals X bar. So it's a little more tight than it was before. So I'm just going to draw a picture so you can see. Right. So this would have been our hypothesis mean is at 100. Okay. So our 1.65, I'll do that in green here. So 1.65, this was our old Z value. So this was 106.58, right? And now we have 109. So we're kind of out here. So this is 109.3. And this gives us a Z value of 2.326. So this was the old Z value. What was our old Z value? 0.05 was at 1.65. Okay. So now we're here. This is alpha equals 0.01. That's that area under that curve right there. Okay, so we've kind of tightened our criteria for significance. We've made it like you had to, these values, our sample means have to be much greater than our null hypothesis mean in order to be considered significantly different. Okay, so now when our true mean is equal to 108, right? So 108 is closer to 109. The power of rejecting our null hypothesis, right? It's our power. That's the probability that X bar is greater than or equal to 109.34 when our true mean is equal to 108. Oh, we bypassed it already. Is equal to power, probability that Z is greater than or equal to 109.34 minus 108 all over same parameters that we had before. Okay, so I plugged in our sample mean that's going to trigger us into the critical region. Our true means at 108, and these was our same standard deviation and sample size as before. So the only thing that we've changed is our alpha value, right? We want to see how that affects things. So probability that Z is greater than 0.326. So that's what I get here. I get 0.326 equal to 1 minus the probability that Z is less than or equal to 0.326. So from my table, 1 minus 0.6278 is going to give me 0.3722, which is our power. Okay, so let's draw out what that looks like. Like, what am I doing here? All right. You don't have to draw these curves when you're doing the homework problems, but it may help you try to understand like what's actually happening. So this is our hypothesis, right? Our mean is equal to 100. And let's draw this out. So then I'm going to put my true mean here, 108. And then our critical region is 109.3. So this is our critical region right here, and our true mean is right there. All right, so now what we're looking at is this part here, and right, this part here gave us that value. This now is our power, which is equal to 0.3722. Okay, so it's a smaller power, right? I mean, like we've actually bypassed our value here. Whereas remember, our former power was like right here. It was much bigger for the same, all the same sets, but a different alpha value, right? Because that alpha value set our critical point over here. So there was more overlap between those two. So let's summarize what it is that we're actually doing here in words. So the probability of a type 2 error, which is 1 minus the power, that's our beta, when alpha equals 0.01 is 1 minus 0.3722, which is equal to 0.6278. That's our beta, which is greater than a type 2 error when alpha was equal to 0.05 and the true mean 108. Okay. We've tightened the statistical value, but that means that we've increased the type 2 error. Okay. So let's see, and then let's add this to our power plot. So what I'm going to do. Okay, hold on to that. I'll come back to that page if you want to see. I'm going to add this to our power plot. Yeah. All right, so I'll do that in a different color. I'll do it in green, just so we can distinguish between them. So now, right, here's our value for 0.05. Now, if I go over to 108, right, I get 0.3 on 1, 2, 3, so 0.3, almost 0.4, 0.372. So this is 108 and 0.372, okay? And then I can extrapolate how things are going to go. So it's going to look like, going to be a steeper curve, and it's going to go up like this. And this is our alpha equals 0.01 and n of 16. We didn't plot these values. We didn't calculate these values here, but this is like the shape of the curve that's going to happen based on this value here. Okay. You guys got that? A lot in this example, but it's good. We just keep manipulating different parameters here and there just to see how things are changing. Okay. All right, so part 3, part 4. So part 5 says, guess what? We get to redo this with an increased sample size. Okay, if I increase the sample size, then maybe I can relax a little bit of my alpha. I'm going to increase the sample size. My alpha goes back to 0.05. We're going to recompute the power for the same hypothesis. We're going to do it for these true means that we have here just to see what we've got. Okay, so let's go back. So I've got alpha equals 0.05, which is z has to be greater than or equal to 1.65, which means n equals 64. So because we've changed the n, that's going to change our x bar again. Changes our x bar. So I have to recalculate my x bar. So z equals 1.65. which is x bar minus 100 all over 16 radical 64, which is going to give me an x bar of 103.29. Okay, anytime I change one of these parameters within my z calculation, right, my alpha, my sigma, or my radical, it's more likely that we're going to be changing n, right, or we're going to be changing our alpha levels. Those are the parameters that we can control, really. Than my x bar, but that point, that threshold point, which is going to push us into the critical region, has to be recomputed. Okay, so now let's do. So now for the true mean equals 108. Okay, we're going to try that out. So we're going to calculate the power. So the power is our probability that z is greater than or equal to 103.29 minus 108. What's the distance between our critical point and our true mean, given our standard deviation and our new sample size? And for this, I get 0.997, which is 1 minus the z of minus 2.355. I'm skipping some steps just so we can just kind of show you the numbers, how they're changing. Okay. When our true mean is equal to 112, right, our power is equal to z greater than or equal to, greater than or equal to 103.29 minus 112, 16 over radical 64, and this is equal to 0.9999, which is 1 minus the z of minus 4.355. Okay, so that would be my z value, right? And this is how I'm calculating the power. Like I said, I'm skipping some steps there. And then c, when the mean is equal, true mean is equal to 116, my probability that z is greater than or equal to 103.29 minus, you can imagine what that's going to be, 16 over radical 64 is equal to, I'm just going to tack on a bunch of more 9s, 9, which is 1 minus z of minus 6.355, right? I'm off the table. At this point, by minus 4.3, I'm off the table. Okay, so I can just, I'm never actually going to get to 1 or to 0, okay? So this z value is going to be super small, but it's an asymptote, right? It goes out to the x-axis. It doesn't quite ever reach 0, but we get super close to it, which is why our power increases here. Okay, so now I'm going to plot this on our table. So you guys have these calculations here. I'm going to flip back to our table. Okay, all right, so back to our table, and I'll do this one in purple. Right, so in purple, I've got, I'm starting off here, and then I've got, this is my alpha equals 0.05, okay, and my n is equal to 64. So here at 108, we said we were right about here, 112. We're basically maxing out, right? So our curve essentially maxes out before we ever get there. So this is alpha equals 0.05. N is equal to 64. So increasing the sample size is a great way of, you know, increasing your power, right? Because I've got more statistical samples to work from. I have greater confidence in what I'm working with, okay? So let's summarize what we're looking at here. So my summary, right? So my sample size, my N value is constant, but alpha changes. And then what we see is we've got a decrease in alpha, but increase in beta. And since beta equals 1 minus the power, right? So we want to be careful about that. So kind of like what we're thinking about here. So as the actual means move away from our true mean, our power increases. Okay, I'm sorry. As the actual mean moves away from this, I'm sorry. This is, as the actual mean, this is our true mean, moves away from our hypothesis, our power increases, which makes sense, right? Because what we're saying is I've got my sample distribution, my true distributions over here. As those get farther and farther apart, our power increases because, right, we're definitely significantly different between our sample size and our true mean value. What usually happens is we look for these, oops, you can't see that. We generally set our power to be around 0.8. That's a good mark. So we'll say about 0.8. So if I've got 0.8 as a power, you know, what do I need to choose for a sample size in order to get, you know, an alpha value of 0.05? Or if I have alpha value of 0.5, my power is 0.8, then I need, you know, 16 samples, say, for example. This is going to change my threshold, where my values are going to flip into the critical region. Okay. Let's see. So we can use that. So we can use this. We can use the power. Let's write that down here. We can use values of alpha and power. We can set those. I can set those. Alpha is 0.05. My power is 0.8 to find n, our sample size. Right. So if I want to have a power at 0.8 and I want to have an alpha at 0.05, how many samples do I need to have? Okay, if my hypothesis is here, say for example, I need to gather 64 samples, or I only need 16 samples, or I need, you know, whatever. Okay, so this is actually how you would end up thinking about it, because we calculated the power based on our sample size and our alpha values, but in reality, what you would be doing is you'd have some hypothesis based on, you know, reading research or reading, you know, kind of seeing what's out there. You'd have some hypothesis about where things are. You'd set your alpha, right? You want to make it 0.05 or smaller. And then you would set your power, like I said, 0.8 is a good statistical marker for it. And then given those values, you need to calculate out what your sample size is going to be so that you can say with confidence, right, things are significantly different at the alpha 0.05 level, and our statistics, the statistics that we're running, have a power of 0.8. Say, for example, 0.8 is a good power marker. Okay. That was a long example, but I wanted to show you how just changing certain variables was going to change our power curves. Okay, and what's our goal for all this stuff here. Okay, so that's functionally the end of 6.4. And what I'll do is I'll scan this in and put this up online so that you guys can have it for reference points. And what I'll do right now is I will